When the circuit is analyzed with a loop current analysis, there are also several special cases. The first is a circuit containing branches of the independent current sources. For such a circuit, we analyze it by the loop current analysis. The first step is to choose loop currents. With regard to such a planar circuit, we may choose its meshes as a set of the independent loops. This is loop 1, loop 2, and loop 3. We know that the loop current analysis is essentially writing a set of the KVL equations. That is to say, we express the voltages of all elements in terms of the loop currents along the directions of the loops. But according to the characteristics of the independent current source, its voltage is determined by the external circuit and cannot be expressed by the current flowing through it. In other words, we cannot express the voltage across this independent current source in terms of the loop currents. So the problem should be encountered when writing KVL equations. How should we deal with it? Recall the similar case of the node voltage analysis. For the independent voltage source, we adopt the approach of adding the number of the variables. That is, we assume the number flowing through it is a certain value. We can also use a similar method here. Adding a variable, that is, assume that the voltage across the independent current source is U. Then we can write the loop equations. Okay, we first write the equation for loop 1. The left side of the equation is the voltage drop across all the resistances. Its self-resistance is R1 plus R2, that is R1 plus R2 times I1. The mutual resistance with loop 2 is R2 because two loop currents flow through R2 in the opposite directions. The mutual resistance should be minus R2, that is minus R2 times I2. It has no common resistance branch with loop 3, so the mutual resistance is 0. On the right side, along the direction of the loop, it should be the voltage rise across all the sources. The two voltage sources are US1 plus US2. But don't forget, in this equation, no terms refer to the voltage drop across the independent current source. So now we might replace the independent current source by an independent voltage source, and its voltage should be U. Along the direction of the loop, it should be minus U. It's relatively simple for the second loop. The mutual resistance with loop 1 is also minus R2, that is minus R2 times I1. Its self-resistance is R2 plus R4 plus R5, that is R2 plus R4 plus R5 times I2. The mutual resistance with loop 3 should be R4, and because the two loop currents flowing through it have the opposite directions, it should be minus R4, that is minus R4 times I3. The voltage rise across all the voltage sources along the direction of the loop is negative US2. Similarly, for loop 3, the mutual resistance with loop 1 is 0, and the mutual resistance with loop 2 is minus R4, that is minus R4 times I2. Its self-resistance is R3 plus R4, that is R3 plus R4 times I3. The right side should be the voltage rise across all the sources along the direction of the loops. Here, the voltage across the independent current source is U. We can treat it as a voltage source. Its voltage rise is U. Well, there are three equations with four variables. In addition to the three loop currents, there is an additional variable U. It's a voltage across the independent current source. So we have to find a new equation. What should this new equation be? We find that the characteristic of the independent current source has not been applied yet. That is, the current flowing through this branch should always be Is. how to express the current of this branch with the loop currents? It should be Is equals I1 minus I3. Now we have 4 equations with 4 unknowns. Of course, we can solve the circuit. Is there any other better way? For example, with the node voltage analysis, if the circuit contains only one independent voltage source, we can reduce the number of the equations by choosing the reference node properly. So with the loop current analysis, is there a similar better way? Of course. Because the independent loops can be arbitrarily selected, and the number is certain, for such a planar circuit, we choose its matches as a set of the independent loops just now. Therefore, the number of the loop currents flowing through the current source is 2. If we can skillfully choose a set of the independent loops so that there is only one loop current flowing through the current source, then the loop current can be determined immediately. For example, in this planar circuit, now we choose such a set of independent loops. This is loop 1, this is loop 2. The third loop no longer goes through the independent current source, but through the peripheral large loop. This is loop 3. Okay, now only one loop current flows through the independent current source. That's I1. According to the relationship between the loop current and the branch current, we can determine I1 immediately. It should be equal to Is. That is great. Since one of the variables have been found immediately. For loop 2 and loop 3, because they no longer go through the independent current source, it is also relatively simple to write their equations. It should be pointed out that because the independent loops are different from what we choose just now, all the self-resistances and mutual resistances of the loops will be changed. Well, in fact, we only need to solve 2 equations now, that is, equations about I2 and I3. It is certainly simpler than the method of adding variables just now. Moreover, this method of selecting a set of proper independent loops is not only applicable to the current containing one independent source, but also applicable to the current with multiple independent sources. As long as the independent loops are selected properly, you can always ensure that there is only one loop current flowing through the independent current source.